Hey, welcome to my new video. Today we're going to talk about rings and fields. I'm gonna give you a bird's eye point of view of rings and fields, and I'm gonna do that by making the connection to linear algebra. I think that is a good first introduction to develop the intuition, because rings and fields can be a bit abstract, but you've likely already seen some linear algebra, so that helps to develop some intuition about what it so means. Okay, so we're going to start with a definition. So a ring is a set R with two operations. We have the operation plus from R plus R to R, and it sends xy to x plus y, and we call that addition. And we have an operation times from R cross R to R, and it sends a pair xy to x cross y, or just x times y, and it's called multiplication. And we have two elements, and these are the 0, which is the additive inverse, the additive identity. That's just a name. And 1 is the multiplicative identity. So this is all the data of a ring, but then you want to satisfy some axioms. First of all, you want that the set R with this binary operation addition and the additive identity is a abelian group. So recall that it means that R is closed under addition, and the addition is associative, and moreover this addition has an inverse. So for every element in R you can find an inverse for the addition in R. So for x in R there is a y in R such that x plus y is 0, and we write y as minus x. Okay, so that's just a side note. And then we have that multiplication is unital. So the multiplication is unital. It means that for all x in R, 1 times x is x times 1 is x. And then we have that multiplication is associative, meaning that for all x, y, z in R, I'm going to take the next line, x, y, z is x, y, z. So if you have any number of elements in R, it doesn't matter in which order you multiply them together. And the multiplication is distributive over the addition, which means that for all x, y, z, w in R, we have that x times y plus z. So this is as you expect it to be. And similarly, from the right, we can multiply with the w, and then we get that it distributes over the addition like this. Okay, so this is what a ring is. We have a set, two operations called addition and multiplication, and these two operations satisfy these rules that it is unital, meaning that we have this multiplicative identity such that it does nothing when you multiply it with any number, and it's associative, meaning that the multiplication It doesn't matter in which order you do it, and it is distributive with the addition, meaning that the normal interaction between these two operations on R hold. And here's a remark. So in general, R is not commutative. So although these rules and other rules which you can deduce from the actions hold in a general ring, what you cannot show for a general ring is that not for all xy in R does xy equal to yx need to hold. So there are rings for which this rule, which normally would hold, you think, in multiplication, does not hold. Okay, so here are a few examples. The first, most basic and trivial example is the so-called zero ring. So take R to be just the singleton 0, and then the addition and multiplication are like this. 0 plus 0 is 0, and 0 times 0 is 0. And it's easy to check that you have all these axioms, because every axiom becomes trivial in this case. And the weird thing is that that 0 is 1 here. And this is also the only example of a ring where 0 can ever be 1. Okay. And now we have another example, the just slightly less trivial example maybe is F2, which is Z2, which is the ring with two elements, 0 and 1, where addition and multiplication are defined as you are accustomed to for Z modulo 2. And we have matrices. In other words, we let Mn over say R be the set of real n by n matrices. With addition is entry-wise. So if you have a matrix, A is Aij, Ij, and B is Bij, Ij, then A plus B is Aij plus Bij, Ij. Ij, like so. Okay, and the multiplication is matrix multiplication. So here's a remark. In general, M and R, so the matrices, n by n matrices, is not commutative. Because you know that in general, A times B is not B times A for matrices. Okay. So another thing that you could remark is that not every matrix is invertible. So there you see an example of a ring where not every element is invertible. Okay. So here is another example. The example of polynomials. You write R square brackets T. You let that be the set of polynomials with real coefficients. So these are expressions of the form a0 plus a1t plus plus antn, where n is some natural number and all the ai are in R. Okay, so here we have the set of polynomials with real coefficients. These are expressions of this form. And now we want to define addition and multiplication. And so that basically goes exactly the way that you are accustomed to for addition and multiplication of polynomials. And observe that here we can think of a polynomial in RT as a polynomial function from R to R. Since we know that if PT and QT are polynomials in RT, then PT is equal to QT as polynomials if and only if for all numbers x in R, the polynomial P evaluated at x is equal to the polynomial Q evaluated at x. So this seems almost trivial, but here is another example to show that this phenomenon, that we can think of polynomials as polynomial functions, is in general special. It's not something which happens in general, because if we look at, take ZT, Z2T, which is now the set of polynomials with Z2 coefficients. So like before, we can write them as A0 plus A1t plus dot dot plus ANt to the n, where n is some natural number, and all the AI are now in Z2, so they are 0 or 1, right? And now this is again a ring with addition and multiplication defined as before, as for R2 RT. So for example, ANt to the n plus BN t to the n is just the sum of AN plus BN t to the n, like so. Right? But now, if we look at the set of, now consider the set of polynomial functions, or I mean, I don't even know what it means, so let's just look at the set of all functions from Z2 to Z2, right? Then we have here the set of all functions from Z to Z2. So let's write S is the functions Z2 to Z2. Then this is a set of functions between two finite sets, right? And then S is finite, because there are only a finite number of functions between two given finite sets. So it follows that Z2t cannot be identified with a set of functions from Z2 to Z2, simply because there are an infinite number of polynomials over here, and there are a finite number of functions from Z to Z2. So in other words, if you have two polynomials with Z2 coefficients, then evaluating them at the point 0 and 1 in Z2 cannot distinguish them. Okay. So those are the examples that I want to give of rings. Oops. Now I want to talk about modules. So rings have a natural thing on which they act. So let's introduce that. Let R be a ring. Then a module over R is an abelian group M with an action R cross M to M, mapping a element in R and an element in M to something new in M, which you write as a lambda times X, such that it needs to satisfy some reasonable conditions. We have that it doesn't matter in which order you multiply elements of R and then an element in M. And likewise, we can take two elements in R, add them together and let them act on X, and it's the same as this for lambda mu in R and X in M. And on the other hand, we can take lambda and two elements in M, and we see that that is also the same like this. And finally, 1 times X is just X for 1, the neutral element in R. Okay, so why am I introducing this? It is because this is going to give us the connection to linear algebra. So here are a few examples. Any ring is a module over itself, where the action R cross R to R is given by multiplication. Okay. And another important example is that any abelian group is a Z module. So we want an action of Z on a given abelian group A, and we do this by mapping n times A to A plus dot 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 plus A, where this is n times. And it's a good exercise, if you've not seen this before, to check that this actually gives you a Z module. So now, to make the connection to linear algebra, we're going to introduce the last definition, namely for a ring R, let the group of units of R, so the group of units of R is the definition here, be, so we write UR for units, or sometimes R cross, to be all y in R, so it is the set of all elements y in R, such that there is an x in R with x times y is equal to 1. Okay. So the remark here is that the group of units R is a group, which is not hard to check. It's associative and it has inverses by definition. And here are examples. So if we take R, which is a ring, where addition and multiplication is just given by addition and multiplication, then if we throw away the 0, then we have the units in R. And if, on the other hand, for Z, so what are the units in Z? That's an interesting question, because you can take, for example, so always 1 is in there. because 1 is always invertible, because 1 times 1 is 1. And also always minus 1 is in there, because minus 1 times minus 1 is 1. But now suppose that any x is in the units of z, then we have a y in z such that x times y is 1. So obviously x is not 0, and x and y are integers, so we can just solve this for the real numbers, for example, and get that y is 1 over x. But if this is an integer, then it follows that x is in 1 or minus 1. Like so. So actually the units in z are 1 and minus 1. Okay. And now we are almost done, because now we can give our tie to the linear algebra, because we're going to say that a field is a ring, is a commutative ring such that, let's call it R, such that if you throw away the 0, you get the units of R. So that's exactly what happens here, right? And that's no mystery, because R is a field. So this behavior is exactly what characterizes fields. It's all those rings which are commutative, such that if you throw away the 0, then you get the units. In other words, every non-zero element is invertible in R. Okay. And now let K be a field. And then a vector space over K, so a vector space over K is nothing more than a module over K. Nothing more, nothing less. So in this way, rings and modules are a generalization of fields and vector spaces, and as such they are a generalization of linear algebra. So I hope that the perspective can help you a bit with processing all these abstract machinery, and good luck and enjoy.